You ever been in a house that is comfortable until you walked by a window? Or how about a house that wasn't really even comfortable ever, despite the furnace running 24/7? Want to know why? I'm Dave Edwards with Earthbound Homes, and today we're talking heat with Building Science Deep Dive. As we discussed in a previous video, the exterior envelope of a house is a structure that separates the inside of your house from the outside of your house, or the outside. It includes the floors, the walls, the roof of any conditioned space in your home. Now, the conditioned space is the portion of your home that is heated or cooled by a furnace or boiler, fireplace, wood stove, radiators, a heat pump, or an air conditioner. It can include your basement, an attic, a garage, or any other space that you heat or cool at any other time of the year. The main function of the exterior envelope of the house is, or any building, is to hold up the structure and to keep the elements out, the wind, the rain, the water, to keep the heat and the cold out, depending on the season, and the occasional critter or nosy neighbor. Now, as you would imagine, the materials that make up the exterior envelope and how they are put together define how it functions as a assembly. For each of the roles it is responsible for, keeping out the cold in the winter or the hot in the summer. That is specifically dedicated to the insulation. Now, every material in the exterior envelope, even air, transfers energy in different ways, and even the arrangement of materials in the walls, the roof, and the floors of the house or the building relates to how that entire assembly performs in reducing energy transfer from inside to outside in the wintertime or from outside to inside in the summertime. The kind of energy transfer is very specific for every different material in the exterior envelope. For instance, air cannot conduct energy, but steel is a great conductor of energy and conducts energy about 300 times better than wood. Conversely, steel beams do not transmit heat through convection, which is the movement of air, but air is actually excellent at it. Now, books have been written on all the different materials, different combinations of and various assemblies of these materials in an effort to develop the perfect wall for the perfect location and situation. Fortunately, you don't have to understand all those books or read them to understand how to build your house better. You only have to understand some basic physics about what heat energy is and how it affects the characteristics of molecules and how it moves in and out in nature. Firstly, heat is just kinetic energy that comes from the vibration of atoms and molecules within a material, or even the rotation of those molecules. In solids, the molecules vibrate only slightly at about 273 degrees Celsius, or minus 273 degrees Celsius, or 0 degrees Kelvin, their equivalent, just different scales, kind of like Celsius and Fahrenheit. These molecules stop all movement and fit tightly together. So at 0 degrees Kelvin, or minus 273 degrees Celsius, there is no molecule movement within a solid material. This temperature is called absolute zero for that specific reason, and is the coldest possible temperature according to physics. Think about this. The void of space just above our planet is about 2.7 degrees Kelvin. So 2.7 degrees Celsius above the point at which all molecules stop moving. Secondly, heat moves only in one direction, from an area of high temperature to an area of low temperature. The difference in temperature between the higher temperature area and the lower temperature area is called the delta T. And the bigger the delta T, the faster heat moves between them. So a high delta T, or a high difference in temperature, causes a rapid movement of heat between the high temperature area and the low temperature area. Now, every material has a unique characteristic called its specific heat capacity. The specific heat capacity of a material corresponds to how much heat it takes to raise that material 1 degree Celsius. So let's use water as an example. The specific heat capacity of water is 4.186 joules. That means that it takes 4.186 joules, which is a measurement of heat, to lift 1 gram of water 1 degree Celsius. Now, a joule is actually compared to what's called a scientific calorie, and a scientific calorie is equal to 4.186 joules. So 1 scientific calorie is equal to the amount of energy that it takes to raise 1 gram of water 1 degree Celsius. Now, a scientific calorie is a bit different than the calories that you're normally looking at on the side of packages. It is actually 1/1000th of a calorie you see on the side of a cereal box, for instance. So, meaning that 1 gram of water heated with 4.186 joules, or 1 scientific calorie, raises its temperature by 1 degree Celsius. So every material has a specific heat capacity. And even ice has a specific heat capacity. You can actually have ice that's minus 100 degrees or ice that's 0 degrees Celsius. And ice, we know, has a specific heat capacity of 2.09 joules, or about half a scientific calorie. So it heats up faster than water does. Steel also has a specific heat capacity of about 0.42, which means it ends up heating up about 10 times faster than water, meaning that steel absorbs about 1/10 of the amount of heat to raise its temperature 1 degree Celsius. Now, as a solid material gets warmer, meaning its molecules absorb energy, its molecules start moving faster and faster, and till they get to a specific temperature where it changes into a liquid. Now, this temperature is also unique to every material. It's called the melting point, or the specific heat of fusion. Now, the melting point of a material is directly correlated to the material components, the chemical makeup of that material. For water, as we know, the melting point is 0 degrees Celsius or 32 degrees Fahrenheit. For steel, it's 1,675 degrees Celsius or 2,200 degrees Fahrenheit, meaning it has a higher melting point or a higher specific heat of fusion. Now, when a material goes from its solid state to its liquid state, it actually undergoes a major chemical change that means that its molecules stop interacting in the same way. In a solid, molecules are very aggregated and closely packed, so they're not moving a lot. In a liquid, they're actually much more random. They move around a lot, they're not connected to their neighbors, their interaction is much more transient. So this molecular change comes from a tremendous amount of energy absorption, which changes those interactions of those molecules with each other. And that increase in movement is called entropy, for a randomness. So they're more random, they move around more. In liquids, this interaction of molecules with their neighbors is transient and disorganized, unlike solids where it's largely fixed, stable, and permanent. Now, that same process happens when a material continues to get heated up. It goes from boiling to an evaporation point where it turns into a vapor. This is called a specific heat of vaporization. And when the material undergoes another phase change from a liquid to a gas, it also absorbs an enormous amount of energy. And what we look at when we look at that phase change, or that change from a liquid to a gas, is extraordinary. Now with water, that phase change happens around 100 degrees Celsius, or as we know, 212 degrees Fahrenheit. But it requires an amazing amount of energy to be absorbed by that water before it can become a gas. In fact, it's about 2,260 joules, or about 540 scientific calories, for that 1 gram of water to turn into 1 gram of gas. Now, 540 times more energy to go from water at, say, 98 degrees to water at 99 degrees than it causes for 1 gram of water to go from 100 degrees at water to 100 degrees at gas. So you're not actually changing the temperature, you're just changing the phase of that water from water to gas. So we also see that with this phase change of this water, we see a dramatic increase in the volume of space that water takes up. So that 1 gram of water, when it's turned into a gas, turns into 1,244 times the same volume as it was when it was water. So if you were to take a liter of water and you were to expand it to gas by giving it a tremendous amount of energy, it would change into 1,244 liters of gas, or about the same amount of volume you would see in 328 gallon jugs. Now, this incredible energy absorption and this incredible difference in the volume is actually super important, because it's the way we power steam generators and turbines that boil water in nuclear power plants, and then it expands into steam, and then that steam pushes the turbines and produces energy. It's also very important when we look at phase change materials in how our houses function and how we make our houses more comfortable. If you're interested in learning more about building science, and in future videos we're going to talk about the ways that heat moves through radiation, conduction, and convection, and how those materials and those characteristics of those materials that we find in our exterior assemblies make our houses more comfortable, more energy efficient, more cost effective to heat and cool, and longer lasting. If you're interested in learning more about building science, follow our projects, hit subscribe, and we show you how to build a better way.